Okay, Rama just sent an email. He is sitting in the train and he will be late by 20 minutes or so. So I simply start. Yeah, this is something which I would not have volunteered to talk about because it's kind of tentative and really on the mathematical side, but Rama wanted me to present it, so I'm going to do it. So it's local versus global risk assessment. So it will be a discussion in terms of convex risk measures, more precisely in terms of conditional risk measures. It will be purely on the mathematical side. So the questions, the concerns are mathematical, as you're going to see in this talk, at least. There is no claim at this stage of financial or economic relevance, although I think at least in some sense, at some point, it may be of some use, at least conceptually. So it's based on 3 papers. One has appeared in statistics and risk modeling. 2 others which you find on my homepage. And even for the first, it's better to look at the version on my homepage because that's a corrected version, which corrects an error in the published version. So you see already the mathematical concern, for example, here in the last one, conditional risk measures. Now, conditional risk measures is, in some sense, a nonlinear version of conditional expectations. So some of the natural questions for conditional expectations, for example, in a dynamic setting, you would be down to martingales. So we will be talking about a nonlinear extension of martingales, and the question is, can you get, for example, convergence theorems along increasing or decreasing sigma fields? So this will be one point which we are going to need and then we are going to use. So the agenda is, I will start with a short summary of what we are going to use, plus some additional comments from convex risk measures. You have had a number of talks dealing with that, for example, Stefan Weber in his talks. So it will be just a short summary. Then I describe the spatial setting in which I then will ask certain questions. The idea is to discuss global risk measures for a large network, but to specify them locally. And then the question is, okay, what does it mean at the global level? Then we are going to focus on the locally law invariant case, where there is one key observation that law invariance combined with spatial consistency in a very general sense, reduces the whole thing to the entropic case, which you may not want to consider. And then the implication is something is a little bit strange about the, at first sight, natural notion of consistency, which I'm going to use. So the question also then is, although I'm not going to address that one in today or tomorrow, what are reasonable, more flexible notions of consistency which give you more freedom? Okay, then nonlinear extension of martingale convergence. You'll need it along decreasing filtrations. And then this is going to be applied to the structure of global risk measures with respect to a given local specification. So we are doing some kind of asymptotics. And then the question of phase transition comes up. Phase transition meaning, a term from the physical context, that the local data, the local specification, does not determine uniquely what is going on globally. And so my initial motive was I had at some point worked on these questions in a context motivated by statistical mechanics, so the theory of Gibbs measures, where phase transition, that was the classical idea by Dobrushin, is characterized by a certain non-uniqueness of probability measures given their local conditional probability. So I wanted to understand the non-linear version of that in the context of risk measures. Okay, so I plan to do the first 3 points today and then the rest tomorrow. Yeah, risk measures, originally in the coherent case, more generally in the convex case, were proposed by Artzner, Delbin, Hébert, Heath, as a way of sort of asking yourself, what do you really want from a risk measure, and motivated by deficiency of the standard tool value at risk. And so it's about quantification of financial risk beyond value at risk. Now, value at risk, as you all know, the structure, it's the smallest amount of capital which should be added to a position to make it acceptable. Now, acceptability here is defined in terms of a probability measure. Now, you want that the probability of a loss is bounded by alpha. That's a specific criterion of acceptability. It assumes that you know something about the probability distribution, that you have access to it. And okay, so you take that specific criterion of acceptability, and then you have this general recipe, take the smallest amount which you have to add to make a position acceptable. Now, in fact, it has turned out to have a much wider scope, this busyness of risk measures. Many interfaces, mathematical, some economic. I'm going to show you one which I personally find particularly satisfying in a minute. So the general axiomatic framework is to define monetary risk as a capital requirement, smallest amount that should be added to make a position acceptable. Now, so we have to fix a class of acceptable positions. There are some basic requirements. It should be saturated from above. In other words, if you have a position and then which is acceptable, and then another one where the monetary outcome is always at least as good as a given one, then that a fortiori should be acceptable. And then there's a requirement of convexity, which is not satisfied by value at risk, which expresses the idea that diversification should not be penalized by the capital requirements. So it's a very general framework. And if you apply that recipe, then you get a functional on positions. Yeah, positions are here described as functions on some basic set omega of possible scenarios. And x of omega is the monetary net outcome if the scenario little omega happens. And by this definition, automatically, this functional will have the following properties. It will be monotone, in the sense that if x always comes out better, then the capital requirement is less. It's what Nicole El-Karoui has proposed to call cash invariance instead of translation invariance. If you add an amount to the position, yeah, then this reduces the capital requirement by exactly that amount. So positions are supposed to be discounted already. And you have this convexity of the resulting functional. Well, at first sight, the convexity requirement of the acceptance set is the convexity of a level set of the functional. So it would be quasi-convex a priori. But combined with the monetary properties, it turns out to be actually convex. In the coherent case, which was the original set of axioms, you also would require that the functional is positive homogeneous, which translates into the property of the acceptance set that it's a convex cone. So if a position is acceptable, you blow it up, it remains acceptable. Now that part I find questionable from a financial point of view. So that was one of the reasons that then we emphasized rather the convex case and the coherent case. Yeah, now since you have a convex functional, you can write down a dual representation in terms of convex duality. And again, so there would be certain linear functionals coming in the dual representation, but the monetary properties of the functional, of the risk measure, will make sure that the only linear functionals which are relevant are those corresponding to taking expectations with respect to some probability measure. So you get a class of probability measures, Q, for each, so that's the class of probability measures which are kind of plausible models you are ready to use. For each such probability measure, you compute the expected loss of the position under Q, but now you take them seriously, these probability measures, to a different degree, and this is specified by a penalty function, alpha of Q. So rho of x is the worst case of this penalized expected loss over some class of probabilistic models. So that's the idea. So Q, class of probability measures on the underlying space of scenarios, and the penalty function takes this form, just specification of the general Fenchel-Legendre transform in this setting. You take, for a given model Q, the expected loss, the worst expected loss over all acceptable positions. So that's the penalty applied to the model Q. Okay, so that's the general setting. So in order to introduce a risk measure, you can either pin down the class of acceptable positions. You can also specify a class of probability measures with a penalty function. And so the interpretation would be a class of stress tests, probabilistic stress tests. It's not that at this general stage, we assume already a probability model. In that sense, it's a framework which admits Knightian uncertainty. You do not have to claim that you have and know a basic probability measure. There is room for a lot of model ambiguity. Probability measures come in through the back door via convex duality, but in a different interpretation, not objective measures, but stress tests you want to consider for this purpose. Okay. Now, from a mathematical point of view, so this story started with the financial interpretation of capital requirements in 1999 with the seminal paper of Artsner, Delbin, and others. But in fact, it has a rich prehistory. Now, one special class of such risk measures are Choquet integrals, as we are going to see. And mathematically, that's a story going back to the 50s. Then, in the actuarial context, in the discussion of actuarial premium principles, already Gerber and Desprez in 1985 had, without using the word, the notion, the mathematical definition of a convex risk measure up to a change of sign as a premium principle. And then the coherent case appears again with different words in the book of Peter Huber in Robust Statistics, and also the representation theorem of coherent risk measures. Now, the one interface I find particularly interesting is to one chapter of microeconomics, namely preferences in the face of risk and uncertainty. Now, this, of course, is a long, classical, and ongoing story in microeconomic theory. What is rational behavior in the face of risk and uncertainty? So you have different positions, X and Y, and you might have preferences. No? So in some case you say, okay, X is certainly not worse to me than Y. Now, under mild conditions, huge literature, the Prof, for example, this preference order admits a numerical representation by some real-valued utility function. And of course, the classical setting is von Neumann-Morgenstern, Savage, Aumann, Enscombe, and so on, where they formulate axioms of rationality, axioms for this preference order, which guarantees that the numerical representation takes place in terms of expected utility. So implicit in your preferences, if they are rational in the very rigid sense of von Neumann-Morgenstern, is A, a probability measure, you may know it or not, a utility function, you may know or not, so implicit in the sense that the numerical representation takes this form, expected utility. So that's the paradigm of expected utility. And then, of course, since then, there's this whole story of behavioral observations, paradoxa, that people don't behave that way, and different attempts to modify the notion of rationality here codified by von Neumann-Morgenstern to take account of deviations. So the normative point of view would be, okay, people may deviate, so that means they should learn. They should be converted to this more enlightened state of mind where they would apply expected utility. That's, for example, not what I believe. I rather believe many of these deviations are rational in some sense, in some reasonable sense, and should be taken seriously. And so there's a whole literature relaxing the axioms of rationality here. So important step was Gilboa-Schmeidler, but then one more step, Maccaroni, Marinacci, Rusticchini in a beautiful paper in Econometrica. And the outcome is the axioms of rationality in this flexible form at the level of Maccaroni, Marinacci, Rusticchini is exactly so that the representation takes place in terms of convex risk measure. So instead of applying an expectation with respect to a known or assumed, maybe subjective probability measure, there should be some convex risk measure. Okay, and since the risk measure focuses on the downside and not on the upside, there's a minus sign here in this representation. In the Gilboa-Schmeidler case, the risk measure will be coherent. In the Maccaroni, Marinacci, Rusticchini case, it will be a general convex risk measure. And so we have the dual representation. And here we see how model ambiguity now comes in. You have a whole class of possible models. You have one utility function. And you take expected utility, but you penalize and you take the worst case of a whole class of probabilistic models. Now, of course, classical risk aversion is captured by concavity of U. That's not necessary for this representation. It can be behavioral U, S function, just as in von Neumann-Morgenstern. It just has to be continuous, increasing. But the convexity of the risk measure captures a very different behavioral feature, namely model uncertainty aversion. This you can illustrate with some of the paradoxal experiments where people have behaved differently from the classical setting. Okay, so in this sense, convex risk measures come in a surprisingly natural form in this kind of discussion. Okay, now law invariance. Law invariance, now we give up for a moment on the idea of including Knightian uncertainty. There we would say, okay, we assume a standard probabilistic setting, and law invariance of the risk measure should mean that rho of x only depends on the distribution of x, the law of x under this given probabilistic model. And so this P here now is assumed to be out there to make sense. In many situations, Definetti would immediately claim doesn't make sense. And the older I get, the more carefully I follow some of the arguments of Definetti. But that's kind of a different story. And it's assumed to be accessible so that you get your hands on these distributions. So that's the law invariant case. In that case, such a risk measure, which a priori is defined on functions, no? On positions defined as real valued functions on a set of possible scenarios, can be identified with a functional just on these distributions, sometimes called lotteries in the literature. And one can now study the properties of this functional lotteries. So Stefan Weber did a thorough analysis on this. And in this case, the general dual representation can be written in a more explicit form. It turns out that rho of x can be written as a supremum over the following objects. You take mixtures of average valued risk, defined as an average of valued risk up to level lambda, or expected shortfall, or tail valued risk, so different names. And you take mixtures with some mixing measures on the unit interval. So this class would be called sometimes spectral risk measures, so a term proposed by Acerbi. Then again, you penalize now at the level of mixing measures, and rho can be represented in this way. So that means that average valued risk turns out to be a basic building block in the law invariant case. Now, everything is some more or less complicated combination of average valued risk. Now here is the interface with classical Choquet theory. You can write some application of Fubini gives you that you can write it as a Choquet integral of the loss minus x with respect not to the underlying probability measure, but a concave distortion. That makes it a capacity, no longer a probability measure, a nonlinear object, and there's a well-known theory of integration with respect to capacities, and that's what you have here. And for each mu, you get a concave distortion function psi mu on the unit interval starting at 0, where the derivative is given in this form. That means C of 1 will be equal to 1. And so that's a distortion function. And it's in fact a concave distortion function because here the derivative obviously decreases. So that's one of the mathematical interfaces. Then recently there has been a lot of discussion in the community of people who look at these risk measures under the slogan of elicitability, Knighting. In fact, there again, it's an old story. It's practically the same as the concept of an M estimator proposed by Huber in the 60s. And one observation, what does it mean? It means that for any lottery in the range of possible lotteries defined by your class of positions, the value of the functional in mu should minimize an expected score if mu actually drives the data. So that should be true for any mu in this class. And then it's a simple observation going back to Osband in 1985 that the functional has convex level sets. And without talking about elicitability, with a different motivation, which I'm not going to explain now, Stefan Weber in his thesis showed that as soon as a law-invariant risk measure has convex level sets, it must be utility-based shortfall risk. What does that mean? There exists a loss function, typically convex if the risk measure is, the original risk measure is indeed convex, but it applies more generally just for monetary risk measures which are elicitable, also to value at risk, for example, and some threshold, L0, such that acceptability is defined by the condition that the expected loss should be below some threshold. Or you can, of course, rewrite it in terms of utility, turning the loss function around into a concave utility function. The requirement is expected utility should be above some threshold. So such risk measures are called utility-based. So the acceptance, the notion of acceptance is given by expected utility, which should be above some threshold. Of course, you could now also reply classical expected utility by something more fancy, a la Marinacci, and so on, to include. So that would go beyond the law-invariant case. But let's just stick to this. So that was one reason also that we pushed the idea of convex risk measures, because that was one of the ways of defining acceptability, which struck us as quite plausible. Okay, and then the penalty function can be computed in this case using convex duality. So L star is the Fenchel-Legendre transform of the original loss function. And you get a class of explicit examples. And here is one, which will play a role later on. If in this approach, you take the classical exponential utility, then this recipe produces what Nicole El-Khoury has proposed to call the entropic risk measure, very simple formula. And it's called entropic because here the penalty function is given by relative entropy. So 1 over beta, if beta is a risk tolerance parameter here in the exponential utility, times the relative entropy of Q with respect to P. Now, the intuition is, this is law invariant, so you have your benchmark model P. But you consider also other models in your computation of the capital requirement, but you penalize them the more they are away from your benchmark model. And being away is quantified by relative entropy. So a specific divergence measure. As soon as you replace here relative entropy by other standard divergence measures, you get the class, a more general class of divergence risk measures, which contains a lot of things, for example, Bental's optimized certainty equivalence. So, okay, a rich fauna of things. Okay, so that was the summary for convex risk measures. Now we turn to a spatial setting. So the idea is to look at spatial risk measures in some large network, discuss local specification, and then do some asymptotics for a large system, and focus on critical phenomena such as phase transition, an analogy to the theory of Gibbs measures in statistical mechanics. So that really is then at this stage a purely mathematical investigation, no claim already that this has immediate relevance. But let's just see how it plays out. So local versus global risk assessment in terms of convex risk measures in a large financial network, financial quotation marks. So we have a set of sites or nodes, and each node can be in some state, in some state space S. And so the situation is described by configurations, little omega. So that's the scenarios. The scenario consists in assigning a state to each node of the network. And then we could summarize at each state by some real-valued random variable, for example, the P&L or just the loss at that node. And then we get a big state space, all vectors, which for each node to give you this real-valued quantity. And now in the discussion of systemic risk measures, so one approach is kind of top-down. You write down conditions for a risk measure applied to this very complex setting, which means to that kind of Banach space. For example, Overbeck takes an LP space here at each node, and then the product of these LP spaces, and then considers convex risk measures on that big Banach space. Typically, there will be a structural decomposition. So that's the basic idea is due to Chen and Maulemi, 2013. Mathematically, kind of an elementary setting. The omega is finite. Overbeck and co-authors have a very nice recent general formulation that's mathematically more appealing. Okay, and the structural decomposition looks like this. Such a systemic risk measure, if you want to call it this way, rho bar, can be decomposed into an aggregation mechanism which associates to this vector a number, aggregates all these xi's into one real number. This will be a concave real-valued aggregation function. And then on top of this is a global convex risk measure in the sense which we have discussed so far. So on the space of real-valued position on the underlying set of scenarios. So that's a general structure theorem. And of course, from an applied point of view, this is where the interest begins. This has to be fleshed out. I'm not going to do this here, but okay, mathematically, you can now look at the dual representation of the systemic risk measure using this structural decomposition, because the lambda is a concave object, and the rho admits the representation here, the dual representation for risk measures. This will now be convex, minus lambda x squared, so it admits a Fenchel by convex duality. I can plug that in, and then in the end you get a dual representation. So it's a little bit simplified. So Overbeck has a very careful analysis what exactly goes on there. So that's the mathematical part. Now the financial picture, bottom up, is mainly the question, what does it mean to aggregate? So what does this lambda actually do in real world terms? What should it do? So these are now bottom up considerations. And then on top of this, once you have specified that, you apply a risk measure, a global risk measure of your choice. So Stefan Weber, I think, has given 2 lectures on this topic, on the specification of, and has mathematically set-valued extension of what I just wrote down, which is very interesting, and contains as a special case what Patrick Cheridito talked about in the second workshop in September on measuring and allocating financial risk. So he specified some aggregation mechanism, and then his choice was for the global risk measure, utility-based shortfall risk measure. So these are ways of fleshing out the general framework. Now, at this point, I'm not trying to do this here, but this is, of course, the really interesting agenda from a applied point of view. But now, one observation in these ways of fleshing this out, I have not yet seen how all the effort which goes into risk analysis locally enters the aggregation. So what I think, in a way, it's forgotten. You simply aggregate and then on top. So my question is, what happens if locally you already have done your homework? How does this enter the global risk assessment? That's the title, local versus global. So I now focus on one specific way of looking at it. So suppose we do local risk assessment in the system. So we go to a given node and we apply some risk measure there. So we determine some capital requirement. Now, if we would do that at each node, just looking at the marginal distribution at that node, what is done a lot in practice, then of course you cannot possibly capture relevant interaction effects going on. So here now I assume that we do that conditionally. So at node I, we do a risk assessment there, given the situation outside, which is not maybe very realistic. I'm not talking realistic here, just conceptually. No, this may be very hard to actually do because it means a lot of stress testing. You imagine different outside environments, and then you see, okay, what would it mean in this node? Formally, it means we have not one risk measure, but a risk kernel, which to each environment, little omega, also little omega only used outside, observed outside, gives a risk measure for that node. So it's a conditional, not a marginal approach in the spirit of COVAR, of Adrian and Bronnermeier, but more demanding in a way. So there it's conditioning on certain events outside, and here it's in principle you want to know the local capital requirement given any possible configuration outside.
Are we assuming there are no choices being made at each node?
Choice?
No choices.
No, the choice is already made. The positions are there. You come as a supervising agency and try to.
Because if I'm a bank, my risk, my choice of what to do depends on my capital requirements. And I have choices that I make in terms of what deals to set up with counterparties that are going to be different. If I have a more stringent capital requirement and I don't. And I bear more of the downside risk.
Okay.
Than if I have a less stringent.
Yeah.
But this is all taken as given the level of risk,
yeah.
And assuming that you can just measure it in a sort of.
Yeah. Which of course is far from being immediately
so
realistic.
This is
you are right.
The exercise you're doing.
Yeah. To turn this stuff into a useful story, one has of course to add a lot of
You can't add
other
everything,
considerations.
but-
Yeah. So, yeah, now we assume that we can do that for any finite subset. Now I'm really getting mathematical. Think of a large system. Locally means some finite subset. In practice, all sets are finite, but that's a little bit like in statistical mechanics. They're also in principle, the systems are finite, and yet one does asymptotics, to look at the situation, so to speak, from outside.
Can I ask another question,
Yeah.
so I understand what's going on? Does this allow, if I have more of a capital requirement, so that I have at my node, a safer position, I'm a better counterparty,
Yes?
does that affect the health of the nodes around me?
Yes.
Oh,
Yes,
okay.
yes,
So that
yes,
is
yes,
allowed.
yes, that's the
So that
whole idea.
interaction is
Yeah.
It's
To really,
unclear to me what interactions.
of the conditioning,
Yeah, what interactions were allowed and which ones
Yeah,
which
yeah,
ones were assumed
yeah,
away. So
yeah.
the decision and the subterfuge in hiding distributions and things like that, those choices are not allowed, but it is allowed that, for example, you have an effect which says that whether or not I can cover my obligations depends on the health of my counterparties.
Yeah,
In the environment generally, that's the point.
yeah.
But it's not,
But one would now need exactly
But
that
it's
sort
exact-
of
but this-
discussion,
but
what to exactly,
it's
which
given
kind
by
of
these exogenous
dependencies.
random variables
Yeah,
whose distributions
yeah,
are known.
yeah. Okay, but this,
Okay.
provides
Just-
some
I just,
general framework
I'm
to
not-
allow for
okay,
a
I'm
lot
not,
of such interactions.
we have to make strong, any useful model has strong assumptions. I'm not objecting.
Yeah,
I have some strong assumptions, I just wanna make sure
yeah.
I understand which ones we're making, today.
Yeah. Now comes something which, in the end, one may decide not to pursue at all, because now I require that these local specifications are consistent in the following sense. In the same sense, those of you who have seen dynamic risk measures, it's a standard consistency requirement. It's the same here in the spatial setting. It would mean the following. If you have a small subset, now given the situation outside, you determine a capital requirement. And now if for two positions x and y, it's always bigger for x, no matter what the environment is. And then you go one step back, use less information, namely the one outside of the bigger set W. This should be preserved, this inequality. Then also at that level, the capital requirement for x should be higher. So if you stare at it and think about it, it looks quite plausible, but it has drastic consequences.
Sorry, you have already aggregated, or the X is the aggregated?
The x could already be a position which involves not just at one side, could be any position now on the whole, depending on the whole.
So you're saying I measure the risk of some subset aggregated, and then I go to larger subset.
Yeah,
And I won't
yeah.
let the monotone.
But the x could already involve others, except outside of V, it's kind of frozen. You assume you know exactly, so the dependence of that, you know exactly. It works like a Dirac measure outside, so formally you can take an x already depending on the whole situation.
So can you show this definition again?
Hmm?
Can you show the definition again?
Hmm?
The consistency, can you show it again?
Previous
Yeah,
page.
yeah. So if V is smaller, then first you apply it here, and then you apply it for the larger set, given the information outside, and that's the same as, it's like consistency of conditional expectations, now it's a level of risk measures. In this formulation here, it looks more plausible, but then you show mathematically that it's equivalent to this. I tell you right away, my feeling now, after having looked a lot here at this consistent case, is that it's somehow too strong. But let me first show what is implied by that. Now, in the special linear case, what does that mean? It means instead of a nonlinear risk measure, you simply take a conditional expectation with respect to a conditional distribution for each finite subset, given the situation outside. And that would be the local specification of a random field. And these, of course, should be consistent at the probabilistic level in this form of spatial consistency. And that's a classical problem in statistical mechanics, where you say, okay, suppose we specify these, not the global probability distributions, but just locally a consistent system of conditional probability distributions. What can we say? That's one way of, for those who come from physics, the DLR equations, which usually are formulated at the thermodynamic level, probabilistically correspond to that. Here is a nonlinear example. A nonlinear example is you take such a probabilistic picture, conditional probability distributions, but you take the entropic risk measures conditionally, in terms of the conditional distributions. So that gives you the entropic local specification with some parameter beta. The limiting case 0 would be the linear case we just had. And that's, of course, locally law invariant, because you're taking an entropic risk measure with respect to a given conditional probability measure. And then you check this is indeed consistent in this sense. Yeah, here you write it down, things cancel. If, and here that's crucial, at each v you might want to assume some parameter beta v of risk tolerance, but they must all be the same, essentially, otherwise it will not be consistent. But if they are the same, then this is a consistent picture in the sense of the preceding definition. Now, two basic problems which were discussed in the linear case, in the DLR theory. In the first place, construction of a local specification in that sense from the one-side risk measures. How arbitrarily can we prescribe the conditional risk measures at the single side so that they patch together to a consistent system for finite subsets? Solution in the linear case, highly non-trivial, even if we are just talking about probability distributions, not risk measures. Dobruschin in the East, Frank Spitzer at the time at Cornell in the West. The one-point conditional probabilities admit a consistent extension if and only if they have a very specific form, namely the form that physicists would write down immediately, namely in terms of an interaction potential. And the way physicists are doing this is the only way which produces a consistent system of conditional probability distribution. That the physicists did not know. The mathematicians had a hard time of proving it, but it turned out this way. So it shows, even in the linear case, not quite easy. In the nonlinear case of conditional risk measures, to me, this problem is still open. I have not really understood yet what is going on. But it's solved in the locally law invariant case, which is coming below. And problem 2, given a local specification, what is the structure now of the set of global risk measures that are consistent with my local specification? Is it unique? Well, or is there a multiplicity at the global level that would correspond to a phase transition? Is there something analogous to the integral representation of global Gibbs measures, so at the probabilistic level, the global object would be just the global random field specified by the local interaction potential. Is there a representation in terms of extreme points, in physical jargon, phases, something like that? Yeah. So here we are thinking of a large network doing something like a thermodynamical limit. Formally, we would admit an infinite system, then look at the finite subset, specify there, and then the question, problem 2, is what is the global structure of global risk measures? Now, to do this, so this problem, I think, is now, I understand now this part. And it uses a construction of entrance boundaries for Markov processes by Eugene Dünken. I mentioned Dünken here because Dünken just died on November 14th, a few weeks ago, at the age of 90. And to make a personal comment, when I was a graduate student, Eugene Dünken was one of my heroes. So I studied the volumes on Markov processes. Then I did my PhD on boundary theory for Markov processes. So I'm coming back to an old interest here. And then I decided to go to Moscow for a year in 67. And there was an exchange program, a procedure for doing that. So there was a group of about 12 people, not just mathematics, physics, chemistry, who were supposed to go and some exchange with the Russian or Soviet Academy of Sciences. And we had to do 2 months of intensive Russian language training and other courses of preparation. And then in September 68, we were supposed to go. So we came all to Bonn with our luggage for a final week of preparation. And then the news came that the Soviet Union had blocked the exchange program after the invasion into Czechoslovakia, because West Germany, in the official version, the official Moscow version, was one of the bad guys in this story. So then, half a year later, came a letter that now I could go. But then I had already decided to take an offer from MIT for an instructor position. And in retrospect, I'm very glad that I did that, because Dünken had felt at this point in disgrace. He was put into an academy institute to minimize his contact with students, and I probably would not have seen much of him if I had gone. Okay, so in the linear case of Gibbs measures, let me maybe skip this now, because because time is running out, we started a little late, so let me show you this. That's an excursion now, before we really turn now to the spatial setting. In the locally law invariant case, a general result on consistency and law invariance. So there is a paper by Cooper and Schachermayer who proves that dynamic risk measures, where the consistency condition is part of the setup, if they are law invariant, must be entropic. So I try to use that argument and to apply it in the spatial setting. And this, for a reason which you're going to see a little later, did not really work. So I had to think again how to do it. And so I used here a very nice paper by Cerreavoglio, Maccheroni, Marinacci, Montruccio, with some additional conditional twist. And that gives a simplified argument. Very general. So suppose we have a law invariant risk measure. We are law invariant with respect to P on some atomless probability space, risk measure, say, on L infinity. That defines a partial order on lotteries, so on probability distribution with compact support, in this case, the distributions of such random variables, in the following way: mu looks better than u if the capital requirement is less. So x here is some random variable with that distribution. I could also write calligraphic R of the mu, would be the same. So that is a partial order. Or I could turn the sign around to have the same direction of the inequality. Now we know, if we can check that this partial order satisfies the classical von Neumann-Morgenstern axioms, then there would be an increasing continuous functions, which would give a numerical representation of this order in terms of expected utility. That translates into the fact that the C of mu, minus the risk measure, is a certainty equivalent with respect to that function u. Not necessarily concave at this point, just continuous. Yeah, simple argument. But C is a certainty equivalent with respect to u, if that is the case. And it's also Cash invariant because it comes from a risk measure. And then there's a classical result from De Finetti, sul concetto di media, which says, okay, then this certainty equivalent must be exponential, including the linear case. And that means, translated into rho is a certainty equivalent up to a sign with respect to the exponential utility functions, and that means it is an entropic risk measure. Crucial condition, the independence axiom. So this argument works if we can check the independence axiom for our partial order. No? And the point is, this follows from consistency. Consistency is so strong that it guarantees for the corresponding order here on lotteries the independence axiom. More precisely, if we have a subsigma field F0, let's say that rho is F0 consistent. If we can find a conditional risk measure ρ0 with respect to F0, such that we have this consistency relation here. Theorem, suppose that the law invariant risk measure rho is F0 consistent for some subfield only, we need one, but it should be rich enough, so this probability space with F0 should still be atomless, and it should leave enough space. So omega Fp should be conditionally atomless given F0, which means, for example, that you can find IID uniformly distributed random variables on this big probability space that are independent with respect to F0. So in this sense, conditionally atomless. Then rho must be entropic. And the proof consists in checking the independence axiom. So it's in a way an economic proof. And the basic idea already appears in this paper I mentioned by Chiriavolio and the others, plus a conditional twist. Yeah, it's probably not much sense to go here through the details, but the point is you check it based on consistency. So here's the independence axiom. You find random variables, x, y, z, with these distributions, and you find them orthogonal to F0. And then you define the set A0 in F0 with probability, whose probability is lambda. And then these convex combinations, which you must compare to check the independence axiom, can be represented as the distributions of these mixed random variables. And so our C is minus rho of the convex combination of the distributions is minus rho applied to the corresponding random variable. And we have to show that this relation here holds. Yeah, and this you prove, and here we get consistency, the consistency requirement. We use it. So since rho admits a conditional risk measure with this consistency relation, we can plug it in. Rho0 as a conditional risk measure with respect to F0 has a locality property, which means you can pull out this information here, which is F0 dependent. Then because x is independent of f0, the conditional risk measure must actually be equal to the absolute. That's a little lemma. And the initial assumption to check the independence axiom is that mu is better than u, so the capital requirement is less. Yeah, so you get an inequality if you plug that y in instead of x, then you trace back, and you get an inequality between this term and that term. And that's simply the fact that you have verified the independence axiom. And as a corollary, of course, you get also the Cooper-Schachermayer result. There you have a big trajectory space for your dynamic risk measure, and just take any time to define your sub sigma field, and then dynamically consistent means that the conditions of the general theorem I just stated are satisfied, and so you prove that the risk measure must be entropic. So what I showed you, this economic proof via von Neumann-Morgenstern, is a static proof without auxiliary Markov chains, Koropat's embedding principle, arguments which are used in the very sophisticated Cooper-Schachermayer construction. But I did not see, when I tried initially how to adapt that line of argument to the spatial setting, then it turned out it's in a way more fundamental what's going on. Okay, so that's what. Maybe that's good enough for today. So tomorrow we will go back to the spatial setting and see what happens then. Okay, then I stop here.
So when you look at the local specification, you're asking to specify the risk of each finite subset given the rest?
Yeah.
And then at the end you specialize to the risk of each node given the rest?
Yeah, that was the first problem. Start just with a way of assessing risk in single nodes. How do we extend it to a finite? And this I understand in the locally law invariant case, because then it must be entropic. And then in the entropic case, if you do it at the one side, you have fixed then the risk aversion parameter, and with this parameter you extend it, as I showed you. In general, I do not know.
So if you consider risk measures based on one's own counterparties, so you have a network of counterparties, and I only know my own counterparty, I don't know the rest of the world. So I can only cook up some number based on what I know from my counterparties. So there's counterparty risk, but I don't know my counterparty. So that's a local specification. So it means that conditionally on my counterparties, I don't care about the rest of the world because I don't know anything about it. So
that would not be enough for this story. No, this story is more in the spirit of a supervising agency who knows more and is in a position to require more and to show me what happens if the following stress situation appears. So ideally for any possible stress situation, which of course is no longer realistic, but it's in the spirit, in that spirit, not the spirit you just proposed.
But if you assume that, each node has a random variable describing the loss, and if these random variables have a factor structure, they depend on some macro variables, then it's enough to know the conditional laws given those factors.
Yes.
Right?
Yes.
So that justifies like stress tests which are conducted based on some global variable GDP. Otherwise, you need more.
Yeah. Actually, What you just said, that the stress tests all refer to scenario at the macro level, that would suggest to rewrite the story in mean field terms. Yeah.
But
Which
it's not
anyway
even
may
mean
be
field
a
in this
good
case. What I'm
exercise.
saying is simpler. It's not even mean field, because if you look at the current bank stress test,
Yeah.
you say you specify a mechanism whereby the macro variables affect the bank portfolio, but there is no reaction of the macro variables to the bank portfolio. So it's not even mean field. It's like a one way.
Yeah.
Mean field is more
Yeah.
sophisticated
Yeah.
because then
Yeah.
you would have to
Yeah.
conduct a joint
But then the
stress test.
feedback would come in the question, what are the global
Yeah, of course.
risks that consistent with that? Yeah.
Okay. Excuse me, can I just ask a question also? So you call this the consistent, were the consistent risk measures when you went
Yeah.
from local to global. So just put it into words, because I'm not a mathematician,
Okay.
so that so basically you're saying that when I have local risk measure, so I measure the counterparty risk,
Yeah.
so I measure my risk condition on the states of my neighbors. And then the risk measure is consistent if the global risk measurement preserves this,
Right.
I mean, takes into account the counterparty risk
Right.
too.
Right.
Okay, so this is basically,
Yeah.
okay.
Yeah.
Okay, great, okay.
But the implication, so if we admit local law invariance, the implication is so strong that one starts to wonder whether one should think of relaxing. Okay.
That's another question.
Yeah.
You said that there is a potential, so so what do you call a potential? Is every risk?
This I'm not even going to need. No, the potential refers to the underlying probabilistic level. If you assign conditional probabilities at each node, then they can be patched together to a consistent probability measure. If and only if already the conditional one-point probabilities can be written in terms of an interaction potential.
2-point interaction.
Yeah, no, and this interaction potential can involve neighbors, can involve, yeah, whatever. Okay, thank you. And I'm sorry, it's really mathematical stuff.